So we just finished the three kind of critical simplest concepts. Simplest is time domain simulator all the time. It's a piecewise linear simulator. All the models are piecewise linear. And this concept of multi-level modeling is really important, particularly as you get more into being able to actually extract the full value of simplest and how it can impact your design process. So next, we're going to look at the accuracy of piecewise linear models. Okay, so let's go, if following along in the documentation, we'll go to topic 1.0.4, accuracy of piecewise linear models. So we know that the modeling is a piecewise linear approximation, and the question is, how good is that approximation? How good can it be? And so with the multi-level modeling, we said depending on your simulation objectives, you want to pick the appropriate level of modeling for your critical components so that you achieve your desired accuracy. And if there's an art to simplest, that's one of the key arts. And you can do it in a very systematic fashion. And for any given system, you can do little experiments to see, all right, for certain Bodie plots, how complex do I need to have my switch models? What do I need to have for my capacitor models in order to get good, accurate results? So what we're going to look now at is a number of examples where we are comparing oscilloscope measured data from the lab and the simplest predictions based on the model. So our first example is actually, it's an Infineon digitally controlled synchronous buck. It's got an output voltage of 1 volt, and the step load goes from 10 amps to 20 amps. So you can see the scope trace in red here for current. The scope trace is in blue for the output voltage. So we can see during this step, the output voltage dips, a little bit, maybe 30 millivolts, and then it recovers. You can see that the blue, the oscilloscope, is a little bit fuzzy, a little raggedy. And the reason is this is a digitally controlled device. So the duty cycle, at any given operating point kind of dithers around an average value. And so the scope traces, they don't trace one on top of the other as they might with a pure analog control circuit. And this is 3 traces of the oscilloscope. It's only 1 trace of simplest. If we did 3 traces of simplest, you could actually see the same kind of fuzziness. It's the model set up to be a pure digital control. But in any event, you can see that if we look at kind of what's the maximum error, it's about half the division, which is 10 divisions, that's 5 millivolts out of a volt. So, it's in the 0.5% range of what the circuit actually is doing. Similarly, if we do a step load decrease from 20 amps down to 10, we can see, okay, there's overshoot. And again, if we look at that difference, it's around half a division, 5 millivolts, 0.5%. Very typical, simplest transient analyses. If we have a good model of the system, we get a really good result. Here we're looking at, in this next example, we're looking at the waveforms of a switching, the main power MOSFET. And this is in a quasi-resonant, it's a valley switching flyback, and it's used in an AC adapter application. And here you can see the input voltage looks like we're at low line, 270 volts I'm in, and You can see we turn on, at the valley portion. So here's the drain to source voltage. Here's the gate to source voltage and the drain current. And so you can see we get really good fidelity here and accuracy. You can see the little Miller thresholds during turn on and the Miller threshold during turn off. The fact that the turn on threshold is higher than the turn off, even though the current is essentially 0 during turn on and 3.5 amps during turn off, this negative difference suggests that the gate resistance is quite substantial. And it's important that you get a good model of it. Okay, so Simplest can do a really good job of modeling switching losses. It does take a little extra effort, and you have to be very careful, because not only do you have to have a good model of the MOSFET, you have to have a good model of the driver. The current, the gate current, modeling that correctly and well is as important as modeling the MOSFET itself well. But if you do both, you can get great results. Okay, and it's not all that difficult. This is a model level 2. This device was a model level 2. There wasn't even a data sheet for it, but I was able to do a few lab measurements as well as, I got a SPICE model that was in the same family, looked to be relatively close, and just modified that based on a few lab measurements. And this is what happened. Okay, this is an example of AC results. So this is the Bode plot. It turns out that this circuit is exactly this one here. Okay, so I'm just gonna, usually it's function F11 or F11, depending on how your computer's set up, but that will center your schematic in your schematic window. And so this self-oscillating circuit is actually one that was published by Delta Electronics, and they were struggling because it's self-oscillating. That means it's variable frequency. The switching frequency changes, but based on line and load. They were struggling to come up with a good way of predicting the AC response, in particular the Bode plot. But they had published the circuit with all the parasitic characteristics of all the critical parts. They published the magnetizing inductance, the leakage inductance, the ESR, the ESL, all of it was there. So we just took their paper, created a simplest schematic, put in the values that they had measured in the lab. And then the red is the gain in the phase that we predicted based on the model. And I remember the day it was in Research Triangle Park in North Carolina. I went and I showed them, okay, you guys published this. We just built it up in Simplest to see how we would do. They looked at our results. They ran into the lab, got the lab notebook with all of their lab data, and then spent the next 10 minutes, point by point, going over, comparing what they had measured with what Simplest was projecting. And this, okay, we'll change the load or change the line, and let's do it again. And then later they shared with me their lab data. But this is very typical, as we were talking about earlier, because Simplest can get such a high degree of accuracy in its solving of the piecewise linear system. It has a very low noise floor. We can inject a tiny AC signal, time domain AC signal, and then without having to worry about injection amplitude, be able to get just outstanding AC results. And so this is not at all unusual. We hear from customers all the time how, what do they call it? They say they shot the Bode plot and then their lab measurements lined up right on top of what they had earlier predicted. So this is typical of the kinds of capability and accuracy that you can achieve with these piecewise linear models. where we adjust the complexity to be sufficient to get the accuracy we need, but we don't go overboard. Kind of with SPICE, sort of the simulation philosophy is you put in all the complexity all the time just in case you need it. Simplest will richly reward you for picking the appropriate level of model complexity for your simulation objective, because what you'll get back is time. The simulations will run so much faster with the lower complexity, but the complexity has to be adequate in order to get your accuracy. But don't overload it. Don't put in the complexity that's not needed for your particular simulation objectives. And so you'll be richly rewarded for that discipline. Okay. All right. Any questions on accuracy?